In the vastness of space, two small spacecraft have ventured further than any human creation before them. Launched over 4 decades ago, these twin explorers have crossed the boundaries of our solar system, carrying with them the hopes, dreams, and curiosity of an entire planet. But what exactly have they discovered in their journey? What secrets of the outer planets did they unveil? And as they drift into the unknown, leaving the warmth of our sun far behind, what do they tell us about the future of humanity in the cosmos? Beyond their scientific mission, the Voyager probes carry a messagey golden record, etched with the sounds and images of Earth, destined to wander the stars for millennia. But who is it really for? And what does it say about us, the people who sent it? As we prepare to say goodbye to these incredible machines, whose signals grow fainter with each passing year, we must ask, what will their ultimate legacy be? Will they continue to inspire us to explore further, or are they simply a poignant reminder of our own smallness in the universe? Join us as we unravel the story of the Voyager, humanity's greatest ambassadors to the cosmos. We'll explore their remarkable journey, the groundbreaking discoveries they have made, and the profound questions they leave us with, as they drift endlessly into the final frontier. Chapter 1. The beginning of a great journey. What made the Voyager mission one of the most ambitious endeavors in human history? In the annals of human history, there are few undertakings as ambitious and awe-inspiring as the Voyager mission. Launched in the late 1970s, these two spacecraft, Voyager 1 and Voyager 2, were designed not merely to explore the farthest reaches of our solar system, but to transcend it, journeying into the vast unknown of interstellar space. Their story is a testament to human ingenuity, curiosity, and the relentless pursuit of knowledge. How did a once-in-a-lifetime cosmic opportunity shape the Voyager mission? The idea for the Voyager mission began to take shape in the early 1960s, as NASA scientists and engineers were envisioning ways to explore the outer planets of the solar system. At that time, space exploration was still in its infancy, with the Soviet Union's Sputnik and the United States' early manned missions marking the dawn of the space age. However, a group of forward-thinking individuals recognized the potential for a much grander journey, one that would take humanity's first steps beyond the familiar confines of the inner planets. One of the most significant factors that made the Voyager mission possible was the rare planetary alignment that would occur in the late 1970s and early 1980s. This alignment of Jupiter, Saturn, Uranus, and Neptune, which happens only once every 176 years, would allow a spacecraft to visit all 4 gas giants by utilizing a series of gravity assists, or slingshots, to boost its speed and alter its trajectory. This concept, known as the Grand Tour, was first proposed by aerospace engineer Gary Flandreau in 1964. The idea was to send a spacecraft on a multi-planet flyby mission, using the gravitational pull of each planet to accelerate it to the next destination. As NASA began to seriously consider this mission, they realized the immense potential it held for expanding our understanding of the solar system. The planets beyond Mars were largely unknown, with only a few observations made by ground-based telescopes. The prospect of sending a spacecraft to directly observe these distant worlds was nothing short of revolutionary. Who were the key players behind the mission's success? The task of designing and building the spacecraft fell to the Jet Propulsion Laboratory in Pasadena, California, under the leadership of Edward Stone, who would later become the Voyager project scientist. Stone, an accomplished physicist, was instrumental in shaping the scientific goals of the mission and ensuring that the spacecraft would be equipped with the necessary instruments to achieve them. What kind of engineering marvel was required to make Voyager a reality? The design of the Voyager spacecraft was a marvel of engineering, representing the cutting edge of 1970s technology. Each Voyager spacecraft weighed approximately 825 kilograms, 818 pounds, and stood over 3.5 meters 11.5 feet tall, with a 3.7 meter 12-foot wide high-gain antenna dish that would be used to communicate with Earth. The spacecraft were designed to be fully autonomous, capable of navigating through the solar system and carrying out complex scientific experiments without real-time input from Earth. One of the most critical challenges the designers faced was ensuring that the spacecraft could survive the harsh conditions of space for an extended period. Unlike previous missions that operated relatively close to Earth, Voyager would be venturing far from the Sun, where solar power would be insufficient to keep its systems running. To solve this problem, the engineers equipped Voyager with 3 radioisotope thermoelectric generators RICs, which convert the heat generated by the decay of plutonium-238 into electricity. These RICs were designed to provide a steady power supply for up to 50 years, allowing the spacecraft to continue operating well beyond their primary mission. The scientific instruments aboard the Voyager spacecraft were meticulously selected to maximize the mission's potential for discovery. Among these instruments were Imaging Science System IS, comprised of 2 cameras, a narrow-angle camera for detailed images and a wide-angle camera for context. These were used to capture stunning photographs of the planets and their moons. Infrared Interferometer Spectrometer IRIS. This instrument was used to measure the temperature and composition of the atmospheres of the planets and their moons. Ultraviolet Spectrometer UVS, designed to study the upper atmospheres and ionospheres of the planets. This instrument also contributed to the discovery of the tenuous ring systems around Jupiter and Saturn. Photopolarimeter System UPS. This was used to measure the intensity and polarization of light, providing data on the texture and composition of planetary surfaces and rings. Plasma Spectrometer Pulse. This instrument measured the properties of the solar wind and its interaction with the magnetic fields of the planets. Magnetometer MAG, used to map the magnetic fields of the planets and to study their interactions with the solar wind. Each of these instruments was designed to be as lightweight and energy efficient as possible, given the limitations of the spacecraft's power supply and the vast distances it would travel. The instruments were mounted on a scan platform that could be oriented independently of the spacecraft's main body, allowing the cameras and spectrometers to focus on targets of interest while the spacecraft maintained its course. What were the stakes during the launch? Voyager 2 was the first to launch on August 20, 1977, aboard a Titan E Center rocket from Cape Canaveral, Florida. Although Voyager 2 was launched first, it was on a slower trajectory that would allow it to visit all 4 gas giants, while Voyager 1, which launched on September 5, 1977, was placed on a faster path designed to reach Jupiter and Saturn first. Despite the name order, Voyager 1 would overtake its twin sister and become the first spacecraft to reach interstellar space. The launches themselves were a tense affair, with the teams at JPL and NASA aware that a single malfunction could spell the end of the mission before it had even begun. Fortunately, both spacecraft were successfully placed into their intended trajectories, and the long journey through the solar system commenced. However, the mission faced immediate challenges. Voyager 2, in particular, encountered issues with its scan platform, which was critical for pointing its cameras and instruments at specific targets. Engineers at JPL worked tirelessly to troubleshoot the problem, eventually developing software patches that allowed the spacecraft to continue its mission without a hitch. What made Jupiter so dangerous for the Voyagers? Another significant concern was the harsh radiation environment around Jupiter, the first planetary target. The high levels of radiation could potentially damage the spacecraft's electronics and instruments, jeopardizing the entire mission. To mitigate this risk, the spacecraft were designed with radiation-hardened components and protective shielding, but the success of these measures could only be tested once the spacecraft arrived at Jupiter. What were the mission's groundbreaking goals? The primary mission of the Voyager spacecraft was to conduct close-up studies of Jupiter and Saturn, their rings, and their moons. However, the mission planners were optimistic that the spacecraft might survive long enough to extend their journey to Uranus and Neptune. This extended mission, known as the Voyager Interstellar Mission, would depend on the spacecraft's continued health and the availability of funding. As Edward Stone, the project scientist, remarked, the Voyager mission was designed to be an extraordinary journey of discovery. We were confident that these spacecraft, if successful, would revolutionize our understanding of the outer planets and provide unprecedented insights into the nature of the solar system. The scientific objectives of the mission were vast and varied. At Jupiter, the goals included mapping the planet's complex cloud structures. Voyager would capture high-resolution images of Jupiter's atmosphere, including the famous Great Red Spot, a giant storm that has raged for centuries. Studying the planet's magnetic field. By mapping Jupiter's magnetosphere, scientists hope to learn more about the dynamics of its powerful magnetic field, which is the strongest of any planet in the solar system. Investigating the Galilean moons. The 4 largest moons of Jupiter, Europa, Ganymede, and Callisto are of particular interest due to their diverse geological features. Scientists were especially curious about whose potential volcanic activity in Europa's ice-covered surface, which might harbor a subsurface ocean. At Saturn, the objectives were similarly ambitious. Examining the planet's iconic rings, the Voyager spacecraft would take detailed images of Saturn's rings, revealing their intricate structure and composition. Studying Saturn's atmosphere. Like Jupiter, Saturn's atmosphere is composed mostly of hydrogen and helium, but with distinct features such as its hexagonal polar storm. Exploring Titan. Saturn's largest moon. Titan was of particular interest due to its thick atmosphere, which is rich in nitrogen and organic compounds. Voyager's instruments would attempt to peer through this atmosphere to study the moon's surface. If the spacecraft successfully completed their primary mission, they would continue on to Uranus and Neptune, where similar studies would be conducted. The mission planners also recognized that the Voyagers might continue transmitting data as they traveled beyond the orbits of the planets, providing valuable information about the boundary of the solar system and the nature of interstellar space. Why did the Voyager mission go beyond just scientific exploration? Beyond the scientific objectives, the Voyager mission had a profound symbolic importance. Each spacecraft carried a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. This record, curated by a team led by Carl Sagan, included greetings in 55 languages, music from different cultures, and natural sounds such as whale songs and thunder. The golden record was a message in a bottle, cast into the cosmic ocean with the hope that, perhaps billions of years in the future, it might be found by another civilization. As Sagan famously said, the spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. How did the Voyager mission change the future of space exploration? The Voyager mission also represented a significant milestone in international cooperation in space exploration. Scientists from all over the world contributed to the design and execution of the mission, and the data collected by the spacecraft has been shared globally, advancing our collective understanding of the universe. The success of the Voyager mission was not just a triumph for NASA, but for humanity as a whole. It demonstrated that we could build spacecraft capable of exploring the farthest reaches of our solar system, and it inspired generations of scientists, engineers, and explorers to dream bigger and reach further. As the Voyager spacecraft continue their journey into interstellar space, their legacy endures. They are not just robotic explorers. They are emissaries of human civilization, carrying our message to the stars. The data they have sent back to Earth has transformed our understanding of the outer planets, and their continued operation offers a glimpse into the mysteries of interstellar space. In the words of Edward Stone, the Voyager mission has exceeded all expectations. It has been a journey of discovery that will continue for as long as the spacecraft remain operational, and perhaps even beyond. The launch of the Voyagers marked the beginning of a great journey on that continues to this day, more than 4 decades later. They are a testament to what can be achieved when humanity dares to explore the unknown, and their story is far from over. As they travel ever deeper into the cosmos, the Voyagers remind us of our place in the universe and our unquenchable thirst for discovery. Chapter 2: Voyager's First Encounters. The Gas Giants. What made Jupiter the first true test for the Voyager spacecraft? As the Voyager spacecraft embarked on their historic journey, their first significant destination was Jupiter, the largest and most enigmatic planet in our solar system. This was more than just a milestone. It was the proving ground for the entire mission. The success or failure of Voyager at Jupiter would determine the future course of the mission and humanity's understanding of the outer solar system. Jupiter was not just any planet. It was a giant, holding more mass than all the other planets combined. The spacecraft had to navigate its immense gravitational field, which could either slingshot them further into the solar system or pull them into a catastrophic descent. Moreover, Jupiter's powerful radiation belts, which were many times more intense than Earth's Van Allen belts, posed a severe threat to Voyager's delicate electronics. Engineers at NASA had prepared for this by equipping the spacecraft with radiation-hardened components, but until they approached Jupiter, no one knew if these precautions would be enough. What were scientists hoping to learn from Voyager's encounter with Jupiter? Before Voyager's encounter, Jupiter was known to be a gas giant with a thick atmosphere, fast rotation, and a massive storm called the Great Red Spot. Ground-based telescopes in previous missions, like Pioneer 10 and 11, had provided some insights, but the planet remained largely a mystery. Scientists hoped Voyager would answer many questions, including: what drives the atmospheric dynamics on Jupiter? What are the exact compositions of its clouds and storms? And what lies beneath its swirling atmosphere? The moons of Jupiter were also a major focus. Io, Europa, Ganymede, and Callisto, known as the Galilean moons, were believed to be fascinating worlds in their own right. Scientists speculated that these moons might harbor diverse geological features, with some even suggesting that it could be volcanically active. However, this was mere conjecture until Voyager could confirm it. How did Voyager surpass expectations with its discoveries at Jupiter? When Voyager 1 reached Jupiter in March 1979, the first images it sent back exceeded all expectations. The spacecraft revealed the planet in unprecedented detail, showing a world more dynamic and complex than anyone had imagined. The Great Red Spot, a storm large enough to engulf Earth, was a churning vortex with intricate cloud patterns and turbulent winds. Voyager's cameras captured not just the red spot, but also countless smaller storms and eddies, each contributing to the chaotic beauty of Jupiter's atmosphere. One of the most astonishing discoveries was made on Io, the innermost of the Galilean moons. As Voyager's cameras scanned Io's surface, they revealed a landscape unlike any other in the solar system. Instead of craters, it was covered with colorful plains and mountains, punctuated by giant volcanoes actively spewing molten sulfur. This was the first time active volcanism had been observed on another world. Io's volcanic activity was so intense that it completely reshaped the moon's surface over short timescales, making it one of the most geologically active bodies in the solar system. Europa, another Galilean moon, also presented surprises. Voyager's images showed a smooth, icy surface crisscrossed with dark lines and ridges. This led scientists to hypothesize that beneath Europa's frozen crust might lie a subsurface ocean, kept warm by tidal forces from Jupiter's immense gravity. The potential for liquid water made Europa a prime candidate in the search for extraterrestrial life, a notion that would drive future missions to the moon. Ganymede, the largest moon in the solar system, was found to have a complex surface with regions of both ancient, cratered terrain and younger, grooved areas, suggesting past geological activity. Meanwhile, Callisto, the outermost of the Galilean moons, appeared to be the oldest, with a heavily cratered surface that had remained largely unchanged for billions of years. These discoveries highlighted the diversity of planetary bodies within the Jovian system, each with its own unique history and characteristics. How did the Voyagers navigate the deadly radiation around Jupiter? The intense radiation belts around Jupiter were a formidable challenge. These belts are filled with charged particles that could easily damage or destroy spacecraft electronics. Voyager was equipped with radiation-hardened components and protective shielding, but the spacecraft's survival through this environment was far from guaranteed. As Voyager 1 and 2 approached Jupiter, they had to carefully time their flybys to minimize exposure to the radiation belts while still capturing the necessary data. The spacecraft's systems were continuously monitored for signs of radiation damage, and mission control on Earth prepared for potential disruptions. Despite the dangers, both Voyagers successfully navigated the radiation belts, allowing them to gather invaluable data on Jupiter's magnetic field and radiation environment. This success not only secured the future of the mission but also provided critical insights into the harsh conditions that spacecraft might encounter around other gas giants. What did scientists expect to learn from Saturn, and how did Voyager's discoveries alter our understanding of the planet? After their triumphant encounters with Jupiter, the Voyager spacecraft set their sights on Saturn, the second largest planet in the solar system and the one most famous for its stunning ring system. Before Voyager, Saturn's rings had been observed from Earth, but their true nature remained a mystery. Were they solid, or composed of countless smaller particles? How thick were they, and what caused their intricate patterns? Voyager was tasked with answering these questions. Scientists also anticipated learning more about Saturn's atmosphere and its largest moon, Titan. Titan was of particular interest because it was known to have a dense atmosphere composed primarily of nitrogen, with traces of methane and other hydrocarbons. Some scientists speculated that conditions on Titan could resemble those on early Earth, potentially offering clues to how life might have originated on our planet. How did Voyager reveal the secrets of Saturn's rings? In November 1980, Voyager 1 reached Saturn, followed by Voyager 2 in August 1981. The images and data they sent back transformed our understanding of Saturn's rings. Rather than being solid, the rings were revealed to be composed of countless particles, ranging in size from tiny grains of ice to larger boulders. These particles orbited Saturn in thousands of individual ringlets, creating a complex and ever-changing structure. Voyager discovered that the rings were not uniform. They exhibited features like gaps and divisions, the most famous being the Cassini division, a large gap between the amber rings. Moreover, Voyager observed peculiar radial features known as spokes, which appeared as dark streaks moving across the rings. These spokes were unexpected and remain one of the most intriguing mysteries of Saturn's rings, possibly caused by the interaction between the ring particles and Saturn's magnetic field. The Voyager mission also provided the first close-up images of Saturn's smaller moons, some of which were embedded within the rings. These moons, known as shepherd moons, were found to play a crucial role in maintaining the structure of the rings, their gravitational influence keeping the ring particles in place and creating some of the gaps observed by Voyager. Why was Titan such a critical target, and what did Voyager discover? Titan, Saturn's largest moon, was perhaps the most anticipated target of the entire mission. Shrouded in a thick, orange haze, Titan's surface had never been seen clearly. Scientists hoped that Voyager's instruments could penetrate this atmosphere and reveal the secrets beneath. Titan's atmosphere was known to be rich in organic molecules, leading to speculation that it might have lakes or even oceans of liquid methane and ethane on its surface. Voyager 1's flyby of Titan was designed to take the spacecraft as close as possible without being pulled into the moon's gravity. As Voyager 1 approached, its instruments focused on Titan, gathering data on the atmosphere's composition and structure. Unfortunately, the thick haze proved impenetrable to Voyager's cameras, leaving the surface a mystery. However, the data collected confirmed that Titan's atmosphere was indeed dense, with surface pressure higher than Earth's, and rich in organic compounds. This discovery heightened interest in Titan as a world that might resemble early Earth in some ways. The possibility of complex chemical processes occurring on Titan's surface and in its atmosphere made it a prime candidate for future exploration. Although Voyager couldn't see Titan's surface, the mission laid the groundwork for later missions, such as the Cassini-Huygens mission, which would eventually land a probe on Titan and explore its mysterious surface in detail. How did Voyager's discoveries at Jupiter and Saturn impact our understanding of the solar system? The Voyager encounters with Jupiter and Saturn were nothing short of revolutionary. At Jupiter, Voyager revealed a world of intense storms, powerful magnetic fields, and a family of diverse moons, each with its own story to tell. The discovery of active volcanoes on Io and the potential subsurface ocean on Europa transformed our understanding of these moons and suggested that the outer solar system could be more dynamic and potentially habitable than previously thought. At Saturn, Voyager's detailed observations of the rings and the discovery of their complex structure challenged previous assumptions and opened new avenues of research. The unexpected features like the spokes in the rings and the influence of shepherd moons added layers of complexity to our understanding of ring dynamics. The exploration of Titan, while limited by the moon's dense atmosphere, confirmed that it was a world rich in organic chemistry, setting the stage for further exploration. These discoveries not only expanded our knowledge of the outer planets but also reshaped our understanding of planetary systems as a whole. The Voyager mission demonstrated the incredible diversity of worlds that exist in our solar system, many of which defy easy categorization. The data collected by Voyager continues to be analyzed decades later, providing new insights into the formation and evolution of planets and their moons. As the Voyagers continued their journey outward, leaving Saturn behind, their mission was far from over. But the legacy of their first encounters at Jupiter and Saturn would endure, forever changing our view of the solar system and inspiring generations of scientists to continue exploring the vast, uncharted territories beyond our home planet. Chapter 3: The Outer Reaches. Uranus and Neptune. Why were Uranus and Neptune the most challenging targets for the Voyager mission? After their groundbreaking successes at Jupiter and Saturn, the Voyager spacecraft faced an even greater challenge: the ice giants, Uranus and Neptune. These planets, lying at the very edge of the solar system, were the least understood of the giant planets. Unlike Jupiter and Saturn, Uranus and Neptune had only been observed from afar, with little detail available. The vast distance and lack of previous close-up studies made these planets a mystery that Voyager was uniquely positioned to unravel. The challenges were numerous. Both Uranus and Neptune are far colder than Jupiter and Saturn, with atmospheres composed primarily of hydrogen, helium, and a higher proportion of ices like water, ammonia, and methane. These factors created unique atmospheric conditions that scientists were eager to explore. Moreover, the greater distances meant that communication with the spacecraft would face significant delays, and the weaker sunlight at these distances made imaging and data collection more difficult. Yet, the potential rewards were immense. Voyager could offer the first detailed glimpses of these distant, icy worlds. What did scientists hope to learn from Voyager's encounter with Uranus? Uranus was a particularly intriguing target. Prior to Voyager, very little was known about this distant planet. Its most unusual characteristic was its axial tilt. Uranus is tipped over on its side, with its axis of rotation almost parallel to the plane of the solar system. This bizarre orientation raised numerous questions. How did Uranus end up in such a tilted position? What effect does this tilt have on its atmosphere and magnetic field? And what might we find on its moons, which had never been closely observed? Scientists were particularly interested in studying Uranus' atmosphere, which was expected to be calm and featureless compared to the turbulent atmospheres of Jupiter and Saturn. The planet's faint rings, discovered by ground-based telescopes just a few years before Voyager's arrival, were also a point of interest. Additionally, Uranus had a large number of moons, some of which were expected to have unique geological features. How did Voyager's discoveries at Uranus change our understanding of the planet? When Voyager 2 reached Uranus in January 1986, it provided the first close-up images of this enigmatic planet. As expected, Uranus presented a strikingly different appearance compared to the other giant planets. Its pale blue-green color, due to methane in its atmosphere, made it look serene and featureless at first glance. But upon closer inspection, Voyager revealed more about Uranus than scientists had anticipated. One of the most surprising findings was related to Uranus' magnetic field. Unlike Earth, Jupiter, or Saturn, where the magnetic field is aligned relatively closely with the planet's rotation axis, Uranus' magnetic field was found to be significantly tilted almost 60 degrees from the axis of rotation. Furthermore, the magnetic field was offset from the planet's center, a discovery that puzzled scientists and suggested a highly unusual internal structure. This tilted and offset magnetic field created a lopsided magnetosphere that varied dramatically as Uranus rotated, providing valuable insights into how planetary magnetic fields can behave under extreme conditions. Voyager also discovered 10 previously unknown moons orbiting Uranus, bringing the total to 20. The spacecraft's images of these moons revealed a diverse array of terrains. For instance, Miranda, one of Uranus' moons, exhibited some of the most bizarre surface features in the solar system, with giant canyons, sharp cliffs, and patchwork regions that suggested a history of intense geological upheaval. These findings challenged existing theories about the formation and evolution of moons in the outer solar system. The spacecraft also studied Uranus' ring system in detail. Although not as spectacular as Saturn's rings, Uranus' rings were found to be narrow and dark, composed of small particles and dust. Voyager's observations provided key data on the composition and dynamics of these rings, helping to refine models of how planetary ring systems form and evolve. What did scientists expect to find at Neptune, and why was it a priority? Neptune, the last of the giant planets, presented a different set of mysteries. With a composition similar to Uranus, Neptune was expected to have an equally complex and possibly active atmosphere. However, its greater distance from the Sun meant even colder temperatures and potentially different atmospheric dynamics. Moreover, Neptune's largest moon, Triton, was one of the coldest known objects in the solar system, and scientists were eager to learn more about this distant world. One of the most compelling reasons for exploring Neptune was its role in the broader understanding of planetary systems. Unlike Uranus, which was tilted on its side, Neptune was more conventionally aligned but was known to have a particularly strong and complex magnetic field. Scientists hoped that by comparing Uranus and Neptune, they could gain deeper insights into the magnetic fields of planets and the processes that shape them. Additionally, the study of Neptune's atmosphere, its rings, and its moons, particularly Triton, was seen as crucial for understanding the diversity of conditions that can exist on ice giant planets both in our solar system and around other stars. What did Voyager 2 reveal about Neptune and its moon Triton? In August 1989, Voyager 2 made its closest approach to Neptune, marking the end of its primary planetary mission. The spacecraft's observations provided a wealth of information, much of it surprising and groundbreaking. Unlike the calm atmosphere of Uranus, Neptune was found to be a dynamic and active world. Voyager 2 detected the fastest winds in the solar system, with speeds reaching up to 100 km per hour, about 300 miles per hour. These winds whipped through Neptune's atmosphere, driving massive storms and creating striking cloud patterns, including the Great Dark Spot, a giant storm system similar in size to Earth. Neptune's deep blue color, more vivid than Uranus, was another feature that intrigued scientists. This color, also due to methane, suggested differences in the planet's atmospheric composition and cloud structure compared to Uranus. The discovery of multiple dark spots, transient storm systems, and high-altitude clouds, called scooters, pointed to a more complex and active atmosphere than scientists had expected, raising new questions about the internal heat sources and dynamics driving these phenomena. Perhaps the most unexpected and significant discovery was made on Neptune's largest moon, Triton. Voyager 2 revealed that Triton had a thin atmosphere of nitrogen and methane, with surface temperatures close to absolute zero, making it one of the coldest objects in the solar system. Despite these extreme conditions, Triton exhibited signs of geological activity. Voyager's images showed icy plains, ridges, and, most surprisingly, geysers erupting nitrogen gas into space, evidence of cryovolcanism, where the lava is composed of volatile substances like water, ammonia, or methane instead of molten rock. Triton's retrograde orbit, meaning it orbits Neptune in the opposite direction to the planet's rotation, also suggested that it might be a captured object, possibly a former Kuiper belt object. This discovery hinted at the dynamic processes that shape the outer solar system, including the capture and incorporation of distant objects into planetary systems. How did the Voyager mission redefine our understanding of the outer solar system? The Voyager encounters with Uranus and Neptune marked the first and, so far, only close-up explorations of these distant worlds. What the spacecraft revealed fundamentally altered our understanding of the outer solar system. Uranus and Neptune, once thought to be relatively similar and uneventful, were shown to be dynamic planets with unique characteristics, from Uranus' tipped-over magnetic field to Neptune's fierce winds and active atmosphere. These discoveries highlighted the incredible diversity of planetary environments that exist within our own solar system and underscored the importance of direct exploration. The unexpected geological activity on Triton, the bizarre terrain of Miranda, and the discovery of new moons around Uranus all demonstrated that even the most remote and seemingly inhospitable worlds could harbor complex and surprising phenomena. The data collected by Voyager at Uranus and Neptune continue to be analyzed by scientists today, providing a deeper understanding of the processes that govern not only these planets but also similar ice giants that are now being discovered around other stars. The success of the Voyager mission at these distant planets solidified its place as one of the most ambitious and successful space missions in history. As Voyager 2 departed Neptune, it began its long journey into interstellar space, carrying with it the wealth of knowledge gained from its encounters with the solar system's giant planets. The mission's legacy is a testament to human curiosity and the relentless pursuit of knowledge, reminding us that even the most distant and challenging destinations can yield extraordinary discoveries. Chapter 4: Beyond the Planets, the Golden Records and the Message to the Stars. Why did the Voyager mission carry a message for extraterrestrial civilizations? The Voyager mission was not just a journey through our solar system. It was also a journey into the unknown, a journey that carried with it humanity's hope of making contact with intelligent life beyond our planet. As the Voyager spacecraft were designed to venture farther than any human-made object had ever gone before, NASA saw a unique opportunity to send a message to the stars. But why include such a message on a spacecraft primarily designed for scientific exploration? The idea was simple yet profound. If Voyager were to be found by an advanced civilization millions or even billions of years from now, it could serve as a time capsule, a record of humanity's existence. This initiative was not merely a scientific endeavor but a symbolic gesture in expression of our curiosity, creativity, and desire to connect with the cosmos. Carl Sagan, one of the key figures behind the Voyager mission, championed this idea, viewing it as an opportunity to encapsulate the essence of life on Earth and share it with the universe. The Golden Records, therefore, became more than just a collection of sounds and images. They became a testament to the human spirit and our place in the cosmos. What was included on the Golden Records, and how were they created? The creation of the Golden Records was a monumental task, requiring the efforts of a team of scientists, artists, musicians, and thinkers from around the world. Led by Carl Sagan and his team at Cornell University, the project aimed to create a snapshot of Earth that could be understood by an extraterrestrial intelligence. But with only a limited amount of space on the records, the team had to carefully select what to include. The records contain 115 images depicting a variety of subjects, from human anatomy to landscapes to everyday life on Earth. These images were chosen to represent the diversity and richness of our planet. Alongside the images, the records feature sounds from nature like the singing of birds, the roar of the ocean, and the crackling of fire, intended to convey the sensory experience of life on Earth. Perhaps the most iconic part of the records is the music. Sagan and his team selected music from different cultures and eras, ranging from Bach and Beethoven to traditional folk songs from around the world. This eclectic mix was designed to showcase the universality of music and its ability to transcend cultural and linguistic barriers. In addition to music and sounds, the records also include greetings in 55 different languages, representing the linguistic diversity of our planet. These greetings range from formal introductions to simple expressions of goodwill, each one a message of peace and friendship. The records also contain a message from then U.S. President Jimmy Carter and Secretary General Kurt Waldheim, emphasizing the hope that this gesture would be seen as an expression of goodwill and a sign of our desire to reach out to others in the cosmos. The records themselves were made of gold-plated copper, chosen for its durability, with a cover that included a diagram explaining how to play the records and the location of Earth relative to known pulsars. This was an attempt to ensure that, even if found by a civilization vastly different from our own, the records could be understood and decoded. The entire package was designed to survive the harsh conditions of space for potentially billions of years, making it the longest-lasting artifact of human civilization. What was the significance of the Golden Records for humanity? The Golden Records were more than just a scientific experiment, they were a statement about who we are as a species. In creating them, the Voyager team had to distill the essence of humanity into a format that could be understood by beings who might not share any common frame of reference with us. This required thinking deeply about what defines us as a species, our culture, our knowledge, our emotions, and our place in the universe. The records symbolize humanity's quest for knowledge and our inherent curiosity. They reflect our desire to understand the cosmos and our place within it, as well as our hope that we are not alone in the universe. The project also forced those involved to consider what aspects of our civilization were most important to preserve and share, leading to a greater appreciation of our planet's diversity and the interconnectedness of all life. The Golden Records also served as a reminder of the vastness of the universe and the fragility of life on Earth. They were a recognition that, while we may be confined to a small corner of the cosmos, our reach extends far beyond our home planet. The act of sending this message into space was an optimistic one, rooted in the belief that the future holds possibilities we can only begin to imagine. How did the inclusion of the Golden Records impact the public's perception of the Voyager mission? The Golden Records captured the imagination of the public in a way that few scientific projects had before. While the primary goal of the Voyager mission was to explore the outer planets, the inclusion of the records gave the mission a broader cultural significance. People around the world were captivated by the idea that a piece of Earth, a piece of humanity, was being sent into the vast expanse of space, potentially to be discovered by other intelligent beings. The records became a symbol of hope and unity, representing the idea that, despite our differences, all humans share a common origin and a common destiny. The project also highlighted the importance of art, music, and culture as integral aspects of our identity, alongside science and technology. It demonstrated that our pursuit of knowledge is not just about understanding the physical world, but also about expressing and preserving the richness of the human experience. The public's response to the Golden Records was overwhelmingly positive, with many people feeling a sense of pride and wonder at the thought of our planet's story being told to the stars. The records became a source of inspiration for artists, writers, and musicians, who saw in them a powerful metaphor for the human journey, both our journey through space and our journey through time. What is the legacy of the Golden Records as Voyager travels beyond the solar system? As the Voyager spacecraft continue their journey into interstellar space, the Golden Records remain as symbols of human achievement and aspiration. Even as the spacecraft's scientific instruments slowly shut down, the records will continue to travel, carrying their message of peace and curiosity to the stars. In many ways, the records have outlasted their creators and will outlast humanity itself, serving as a time capsule of our civilization. The legacy of the Golden Records is one of optimism and exploration. They represent the best of what humanity can achieve when we work together, transcending national boundaries and cultural differences. The records are a reminder that, despite the challenges we face on Earth, we are capable of incredible feats of creativity and collaboration. The Golden Records also continue to inspire new generations of scientists, artists, and dreamers. They remind us that our actions today can have an impact far beyond our lifetimes, and that the pursuit of knowledge is a noble and enduring endeavor. As Voyager sails into the unknown, the records it carries serve as a beacon of hope, a testament to the human spirit, and a reminder that our story is just beginning. How does the story of the Golden Records influence our vision of the future? The Golden Records challenge us to think about the future in ways that go beyond the immediate concerns of our daily lives. They ask us to consider the long-term survival of our species, the preservation of our knowledge and culture, and the possibility of making contact with other intelligent beings. In a world often focused on short-term goals, the records are a reminder of the importance of thinking big and looking far into the future. As we continue to explore the universe and search for signs of life beyond Earth, the Golden Records serve as a symbol of our readiness to engage with the cosmos. They represent a future in which humanity is not confined to a single planet, but is an active participant in the greater universe. The story of the records encourages us to dream, to explore, and to reach out to the unknown with open hearts and minds. In the end, the Golden Records are more than just artifacts, they are a legacy of our time on Earth, a message of hope sent across the cosmos, and a testament to the enduring power of human creativity and curiosity. As long as they travel through space, they will continue to carry our story, and the story of our small, fragile planet, into the infinite expanse of the stars. Chapter 5. The Long Goodbye. Voyager's Farewell to the Solar System. What happens when a mission outlives its original purpose? As the Voyager spacecraft continued their journey beyond the outer planets, they entered a phase of the mission that no one had ever experienced before, a journey into the vast, uncharted regions of interstellar space. Originally designed to explore Jupiter and Saturn, the spacecraft had surpassed all expectations, visiting Uranus and Neptune, and sending back data that revolutionized our understanding of the solar system. But now, as they drifted farther from the sun, the question arose: what happens when a mission outlives its original purpose? What becomes of these lonely explorers as they move into the dark, empty spaces between the stars? The answer is both awe-inspiring and melancholy. The Voyagers, once the cutting-edge marvels of human ingenuity, now face an existence of quiet solitude, far from the planets they were designed to study. With each passing day, they journey deeper into the unknown, their signals growing weaker, their instruments aching, and yet, they continue to send back data, revealing secrets about the edge of the solar system that we never imagined. But as they do so, a sense of finality looms over them, a realization that their mission, once filled with discovery and excitement, is slowly coming to an end. Why is the edge of the solar system so foreboding? As the Voyagers approached the boundary of the solar system, known as the heliopause, they entered a region of space that is unlike anything encountered before. The heliopause is where the solar wind, a stream of charged particles emitted by the sun, collides with the interstellar medium, the thin gas and dust that fills the space between stars. This boundary is the true edge of our solar system, a place where the influence of our sun finally gives way to the vast, cold emptiness of interstellar space. Crossing this boundary was a monumental achievement for the Voyagers, marking them as the first human-made objects to leave the solar system. But it was also a moment filled with uncertainty and trepidation. The environment beyond the heliopause is harsh and unforgiving. Temperatures drop to near absolute zero, radiation levels are higher, and the darkness is deeper than anything we can imagine. The spacecraft, designed to operate within the relative warmth and protection of the solar system, now face an environment that tests their endurance to the limit. For the Voyagers, this crossing was not just a physical journey but a symbolic transition from the known to the unknown, from the realm of planets and sunlight to the endless night of interstellar space. It is a place where no light from the sun can reach, where the stars are distant and cold, and where time itself seems to stretch on into eternity. The spacecraft, once beacons of human achievement, are now silent sentinels in a realm of infinite darkness. How do the Voyagers continue to survive in such extreme conditions? Survival in the void of interstellar space is no small feat. The Voyagers were built with durability in mind, but they were never meant to last this long. Over the decades, their power supplies have dwindled, and their instruments have aged. Each year, mission engineers must make difficult decisions, turning off non-essential systems to conserve the remaining power. The once vibrant spacecraft, brimming with sensors and cameras, are now shadows of their former selves, operating with only the bare minimum needed to send back data. The spacecraft rely on nuclear power, generated by radioisotope thermoelectric generators (RICs), which convert the heat from the decay of plutonium-238 into electricity. But even these power sources are not infinite. As the plutonium decays, the power output decreases, forcing mission controllers to shut down instruments one by one. The once powerful signals sent back to Earth are now faint whispers, requiring the most sensitive radio telescopes to detect. Communication delays, already long due to the vast distances, have stretched to over 20 hours for a single round trip, making real-time interaction impossible. Yet, against all odds, the Voyagers persist. Their longevity is a testament to the skill of the engineers who built them and the dedication of the teams who continue to manage their operations. Each piece of data they send back is a small Victoria glimpse into the farthest reaches of space, a reminder of their enduring legacy. But as the years pass, the inevitable looms. The day will come when the power runs out, when the spacecraft falls silent, and their journey continues in darkness, alone and unobserved. Why does the thought of losing contact with the Voyagers evoke such a sense of loss? The Voyagers are more than just machines. They are symbols of human exploration and the desire to push beyond the boundaries of what is known. For over 4 decades, they have been our eyes and ears in the outer solar system, sending back images and data that have reshaped our understanding of the cosmos. They have traveled farther than any other human-made objects, carrying with them the hopes and dreams of generations of scientists, engineers, and dreamers. The prospect of losing contact with these spacecraft is deeply emotional. The Voyagers have been with us for so long, their journeys so intertwined with our quest for knowledge, that the thought of them drifting silently through space, no longer able to communicate, feels like losing a part of ourselves. It is a reminder of the impermanence of human endeavors, of the fact that even our greatest achievements are subject to the relentless passage of time. There is also a profound sense of loneliness associated with the Voyagers' final fate. As they continue to move farther away, they will eventually reach a point where their signals are too faint to detect, where they are too far from any star to be illuminated. They will become cosmic relics, floating in the dark, carrying the golden records as the last remnants of a civilization that may no longer exist by the time they are found, if they are ever found. What is the ultimate fate of the Voyager spacecraft? The ultimate fate of the Voyagers is a sobering thought. In the cold emptiness of interstellar space, they will continue to drift for billions of years, long after their power has faded and their instruments have gone silent. They will pass by distant stars, moving at a slow, steady pace, unaffected by the passage of time. These spacecraft, once symbols of human achievement, will become ghost ships, carrying a message from a distant past into an uncertain future. It is possible that one day, millions or even billions of years from now, another civilization might discover one of the Voyagers. They might decode the golden record, learning about a species that once existed on a small, blue planet orbiting an unremarkable star. But that is a hope shrouded in uncertainty. The vastness of space and the unlikelihood of such an encounter mean that the Voyager's journey is likely to continue in solitude, with only the stars as silent witnesses to their passage. For now, though, the Voyagers are still with us. They still send back data, still offer glimpses of the mysterious regions beyond our solar system. But the day is approaching when that connection will be lost, when the final transmission will be received, and the Voyagers will be left to their endless journey through the void. How do we find meaning in the Voyager's journey as it comes to an end? The story of the Voyager spacecraft is one of exploration, discovery, and ultimately, letting go. As we prepare to say goodbye to these incredible machines, we are reminded of the transient nature of all things. The Voyager's journey, while extraordinary, is a reflection of our own an exploration of the unknown, a quest for knowledge, and an acceptance of the inevitability of endings. But there is also a profound beauty in the Voyager's fate. Their journey into interstellar space is a testament to human curiosity and our desire to reach beyond the limits of our understanding. Even as they move into the darkness, they carry with them the legacy of a civilization that dared to dream, to explore, and to communicate with the stars. In the end, the Voyagers remind us of our place in the universe, small, fragile, and fleeting, but also curious, creative, and capable of great things. Their mission may be coming to an end, but their story will continue to inspire generations to come. As they drift into the unknown, they leave behind a legacy that will endure long after their final signals have faded, a legacy of exploration, of discovery, and of the enduring human spirit. Chapter 6. The Legacy of Voyager. Inspiring future generations. What does the Voyager mission leave behind as its greatest legacy? As the Voyager spacecraft journey further into the unknown, leaving the solar system far behind, we are left to reflect on the legacy they have created. What began as a bold endeavor to explore the outer planets has transformed into one of the most significant achievements in human history. But beyond the scientific data, the images of distant worlds, and the profound discoveries, what is Voyager's greatest legacy? Voyager's most enduring legacy is its embodiment of human curiosity and our unyielding desire to explore the cosmos. The mission has shown that even with the limitations of technology, we can push the boundaries of the possible, venturing beyond the safety of our home planet to uncover the mysteries of the universe. The success of Voyager has inspired countless scientists, engineers, and dreamers to look up at the stars and ask, what else is out there? It is this spirit of exploration that drives us to continue reaching for the stars, to seek knowledge not just for its own sake, but for the betterment of humanity. The golden records, carried by both Voyager 1 and Voyager 2, serve as a message in a bottle, drifting through the cosmic ocean. They encapsulate the essence of our world, offering a glimpse of who we are and what we aspire to be. They represent a hopeful gesture, a statement that even in our small corner of the universe, life exists and it seeks to make contact, to share its story. This message, however unlikely it is to be found, is a testament to our optimism, or belief that we are part of something larger, something cosmic. How has Voyager influenced the next generation of space exploration? The Voyager mission set a high bar for future space exploration. both in terms of technical achievement and scientific discovery. The spacecraft demonstrated that with ingenuity and determination, we can overcome the vast distances and challenges of space travel. This has had a profound impact on the development of subsequent missions, such as the New Horizons mission to Pluto and beyond, the Juno mission to Jupiter, and the upcoming Europa Clipper mission, which will study one of Jupiter's most intriguing moons. Voyager's success has also fueled the dreams of space agencies and private companies alike, inspiring new missions that aim to explore not just our solar system, but other star systems as well. Projects like the Breakthrough Starshot initiative, which seeks to send small, light-powered spacecraft to our nearest stellar neighbor, Proxima Centauri, are direct descendants of the Voyager spirit. These new missions build on the foundation that Voyager laid, pushing even further into the unknown. Moreover, Voyager has played a crucial role in educating and inspiring the public about space science. The images of Jupiter's swirling storms, Saturn's majestic rings, and Neptune's vibrant blue hue have captivated millions, igniting a passion for space in young minds around the world. Documentaries, books, and educational programs about Voyager continue to engage and inspire, ensuring that the mission's impact is felt far beyond the scientific community. What does the future hold for space exploration, and how does Voyager fit into that vision? The future of space exploration is bright, filled with possibilities that were once the realm of science fiction. As we stand on the brink of a new era in space travel, with missions planned to Mars, the Moon, and even asteroids, the lessons learned from Voyager remain invaluable. The mission has taught us about resilience, about the importance of long-term thinking, and about the value of exploration for its own sake. One of the most exciting prospects is the search for life beyond Earth. The discovery of potentially habitable moons like Europa and Enceladus, which have subsurface oceans beneath their icy crusts, has reinvigorated the quest to find extraterrestrial life. Missions like the Europa Clipper, set to launch in the 2020s, aim to explore these moons in detail, searching for signs of life in places we never thought possible. Voyager's discoveries have laid the groundwork for these missions, showing us that the solar system is full of surprises and that life could exist in the most unexpected places. In the broader context of interstellar exploration, Voyager represents the first step in a journey that humanity is only beginning to undertake. As our technology advances, we may one day send more sophisticated probes to other star systems, equipped with the capability to analyze exoplanets and search for signs of life. Voyager's pioneering journey has shown us that the universe is vast, mysterious, and full of potential. It has instilled in us a sense of wonder and a drive to explore further, to push beyond the limits of what we know. Why is it important to continue exploring the cosmos? Exploring the cosmos is not just about answering scientific questions, it is about understanding our place in the universe. It is about pushing the boundaries of human knowledge, challenging our perceptions, and inspiring generations to come. The Voyager mission has shown us that exploration is an essential part of what it means to be human. It is in our nature to ask questions, to seek out the unknown, and to strive for answers, no matter how distant or difficult they may be. Continuing to explore the cosmos is also crucial for the future of humanity. As we face challenges here on Earth, such as climate change, resource depletion, and geopolitical tensions, looking to the stars can provide us with new perspectives and solutions. Space exploration has already led to technological advancements that benefit life on Earth, from satellite communications to medical technologies. Moreover, the possibility of finding other habitable worlds could one day ensure the survival of our species, offering new opportunities for growth and expansion. But perhaps most importantly, space exploration reminds us of our shared humanity. The images of Earth taken by Voyager, the pale blue dots suspended in a vast, dark cosmos, have become iconic symbols of our fragility and our interconnectedness. They remind us that, despite our differences, we all share the same home, the same planet, and the same fate. As we continue to explore the cosmos, we are reminded that we are all part of the same story, a story that began with Voyager and will continue for generations to come. What can we learn from Voyager's journey as we look to the future? Voyager's journey is a powerful reminder of the importance of perseverance, curiosity, and hope. The spacecraft, built with 1970s technology, have defied the odds, traveling farther and lasting longer than anyone ever imagined. Their success teaches us that, with vision and determination, we can achieve the extraordinary, even in the face of uncertainty and adversity. As we look to the future, Voyager's legacy challenges us to think big, to dream beyond the confines of our current capabilities, and to embrace the unknown with courage and curiosity. It reminds us that exploration is not a destination, but a journey on that requires us to constantly push the boundaries of what is possible. Voyager's journey also teaches us about the importance of collaboration. The mission was the result of the combined efforts of scientists, engineers, and visionaries from around the world, all working towards a common goal. As we face the challenges of the future, whether in space or on Earth, the spirit of collaboration will be essential. How does the Voyager mission inspire hope for the future? The Voyager mission, despite its inevitable end, is a beacon of hope. It shows us that even in the vastness of the universe, in the face of overwhelming challenges, we can achieve something remarkable. The mission's success gives us hope that we can continue to explore, to discover, and to learn. It gives us hope that, no matter how dark the journey may seem, there is always light on the horizon, new worlds to explore, new knowledge to gain, and new frontiers to cross. As the Voyagers continue their silent journey into interstellar space, they carry with them the hopes and dreams of all humanity. They remind us that our story is far from over, that there are still countless mysteries to unravel, and that the spirit of exploration that launched them into the cosmos will continue to guide us as we venture into the future. The legacy of Voyager is not just about where we have been, but where we are going. It is about the endless possibilities that lie ahead, the new worlds yet to be discovered, and the knowledge that the journey of exploration will continue, driven by the same curiosity and determination that launched Voyager into the stars. And as we continue to explore, we carry with us the hope that, one day, we will find our place in the vast, beautiful, and mysterious universe that Voyager has helped us to begin to understand.